Welcome everybody to this special session on algebraic effects. And we will have 3 invited talks in this session, each of 40 minutes, including Q&A. And our first speaker is Sam Lindley. And Sam is currently a reader in program language design and implementation at the University of Edinburgh. He has done a significant body of work on effect handlers, especially on language design, as well as effects for efficiency. And in this talk, Sam will tell us about a recent development he has been driven on extending WebAssembly with effect handlers. And that sounds really cool, and I'm very much looking forward to the talk. So take it away, Sam.
Thank you very much, Ning. Just checking you can hear me.
Yes.
Excellent. Good. Yeah, so I was very honored to be invited to speak at this session. I wasn't entirely sure what to speak about, but Ning suggested I talk about this work on WebAssembly, which, because, well, it is something I've been actively working on for a while. It's maybe slightly outside the scope of typical MFPS talks, but I blame Ning for inviting me to talk about this, if anyone has any problems with it. But on the other hand, it is all fundamentally based on mathematical foundations, even if I'm actually talking more about an application of that. So yeah, this session, oops, is this, just trying to get my slide transitions working. Okay. So this session is on algebraic effects. My work is based on effect handlers, which come out of algebraic effects. I'm going to split the talk into 2 parts. So the first part, I'm going to basically talk about effect handlers from the point of view of programmers as a programming abstraction and as a practical device. I will introduce several different forms of effect handlers. Deep handlers, which are the original formulation that comes out of algebraic effects. Shallow handlers, which is another common formulation, and then their synthesis, which Stephen Dolan called sheep handlers, as in a combination of shallow and deep. And the reason I'm introducing those is because they're the ones that we've used as the basis for our extension of effect handlers in WebAssembly. Okay, so yeah, I'll just give my sort of high-level overview of effect handlers. Starting off, sorry?
Oh yeah, okay. No, that's good. I didn't see the slides move, but now it works for me. Okay.
You see them moving now, good. Yes, so first, let's start off thinking about, well, what are effects? A nice kind of idealistic model of programs is as black boxes, where you just have inputs and outputs, and you can't observe anything about the internal computation that goes on. Programs are just mathematical functions. In practice, it's useful to have richer notions of programs where you have some interaction with the environment, and then typically we do this via an operating system. So you don't talk directly to the outside world, we go through some abstraction, or a runtime or an operating system or such like. Lots of different kinds of effects, which I'm sure most of you are familiar with. And kind of the perspective I'm coming from here is thinking about how mainstream people use effects, mainstream programming languages use effects. And typically they're hardwired into implementations. So you have ad hoc implementations of specific effects, which is a pain for a whole load of reasons. You often end up re-implementing the same thing over and over again. In particular, the application I'm particularly concerned with is concurrency and web applications. This is where WebAssembly comes in. And if you take JavaScript, for instance, there are many different, or several different concurrency abstractions, all of which are rather rigid and hardwired into the implementation. So they have generators and iterators, they have promises, they have async await, And all of these things are maintained separately, but there's a lot of commonality to them. So this is where effect handlers come in. They provide a very general way of implementing these kind of features inside your programming language, meaning not just for talking directly to the outside world, but you might implement features as if you had an interaction to some outside context. So yeah, Gordon and Mattia introduced the theory of algebraic effects, which I'm sure that the later talks will cover more, maybe more theoretical aspects of later. And handlers, sorry, Gordon and Mattia introduced handlers on top of the theory of algebraic effects. And they provide a composable and customizable user-defined interpretation of all kinds of effects. So if people aren't familiar with effect handlers, they're quite similar in flavor to other things you may be familiar with, like resumable exceptions, monads, and delimited control. Particularly, they give you direct access to the current context, and that's where their real power comes from. Where they differ from some of these other abstractions, at least from a programming point of view, is their support for composability in particular. And they're not just of theoretical interest, they're actually having quite significant practical industrial interest at the moment. So, for instance, GitHub has this semantic library which is used for doing code analysis, and whenever a pull request takes place, it uses this to generate code navigation. Similarly, a lot of the React library in JavaScript is, although it doesn't directly use effect handlers or algebraic effects, it's directly inspired by these things. And then Pyro has this probabilistic programming language which actually builds in effect handlers for abstracting over different modes of statistical inference. Okay, so this is the high-level picture. One way I like to view effect handlers in a sort of practical setting is as a form of composable user-defined operating systems. So we can expand this box at the top here, which you can view as kind of your program, by basically you write the user program, and that, instead of talking directly to the operating system, it can perform effects according to some interface, and then they plug into these little user-defined operating systems, and these things are effect handlers, and they compose very nicely. And then eventually you might have handlers that perform effects that go directly to the operating system. So yeah, this is all quite hand-wavy and high level so far, but this is kind of the big picture view of what the way I see effect handlers as a programming abstraction. So now I'm going to just give you an overview of a simple operational semantics for the standard deep handlers. I will then show you a couple of variations on this and give you some examples before I flip over to the low-level WebAssembly perspective and how we can apply this design in a completely different context. So yeah, I'm assuming we have a call by value, fine-grained call by value lambda calculus, say. I'm omitting the rules that have nothing to do with computations and just considering let and handling. So we have the reduction rule for let is just the standard one. The crucial thing that we have with handles is that we can handle some computation, a suspended computation, using a handler, which is very similar to an exception handler. So it has this form, you have a return clause which says what to do when you finish your computation and you get a value back. And then you have a number of operation clauses. So think of these as being analogous to exceptions. And in where they actually come from is the theory of algebraic effects. So these things correspond to algebraic effects. And each one of these clauses says what to do if you come across one of an operation in a particular context. Oops. Okay. Component here. So the P is just the parameter, so the payload for the effect or the exception. R corresponds to the resumption or the continuation. And if we look at the return rule, we have a rule here that says, well, if we just have a value, then you take the body of the return clause and substitute in the value for the variable x. But this is where the interesting stuff happens. If you actually have one of these operations, then it depends on what evaluation context. Then you actually capture the evaluation context up to the handle construct. I don't know why my slides keep automatically moving themselves. Sorry about that. So then we proceed with the body of the operation clause, substituting the value for the parameter, but we also substitute in a function value here for the resumption. And this is basically just encapsulating the evaluation context, except as well as doing that, it wraps the same handler around that context. So what that does is it ensures that any subsequent operations will be handled uniformly in the same way. And I've got this side condition here, which is just ensuring that there are no other intermediate handlers in the evaluation context that could handle that operation. So it's just like with exception handling, it bubbles up to the nearest enclosing handler, and that's the one that handles it. But the crucial additional power we get as compared with exception handling is we have access to this resumption. And I'll illustrate that with an example in a minute. But in particular, this gives you a nice way of implementing all kinds of different notions of concurrency directly in your programming language. I'm going to give you a brief overview of an effect type system you can build on top of this, although we're not actually going to really make use of this because we don't have an effect type system for WebAssembly. But basically, the effects types just track all of these operations. Each operation has a parameter type and a result type. We have computation types, which consist of value types paired with effect types, such as a computation of this type will return a value of type A, and it may perform operations in E. So then the rule for performing an operation gives you back the result type of the operation, and the effect must include that operation, and the parameter type must match up with the expected type. And then handling is just like a form of application with this special arrow type here that goes between computations. So a handler takes one computation type to another. And then this is where all the work happens. And it's pretty much typed as you'd expect. I guess a crucial thing to look at here, which distinguishes deep handlers, is that the resumption type returns the final return type of the handler, which mirrors this idea that the body of the resumption is handled by the same handler. So I'm going to just drill down into this here. So this is that rule again, and there's the reduction rule for deep handlers. The other forms of handlers, all the other rules are the same. So that's why I've identified these rules. As I said, the body of the resumption re-invokes the handler here, and that corresponds to having the return type be D here. And essentially all that an effect handler is doing is it's performing a fold over the structure of the computation tree that arises from performing these operations. So the nodes of this tree correspond to operations, the edges correspond to the return types of those operations, and the leaves are the final return values. So the fact that this reduction rule is recursive, that embodies this fold here. So I'll contrast this now with shallow effect handlers. So the things that have changed in the typing rule, instead of returning the D here, we're returning the original effect type. And we're not, and correspondingly, we don't wrap the handler around the evaluation context. So that means if you want to keep on handling the operations uniformly, you have to do that manually. So you typically have you have to do your own recursion, and we'll see that when I show you an example. So yeah, these are the points I just made. The resumption doesn't re-invoke the handler, and right. So essentially, what this is doing is it performs a case split on this, the computation tree that arises from these operations. Yeah, if you're not familiar with algebraic effects and handlers, but you are familiar with free monads, think of the structure that you're traversing here as the free monad structure. It is the free monad structure over the functor generated by the signature of the operations that you're considering. Right. So now I'll show you this slightly quirky construction, sheep handlers. So this is a hybrid of shallow and deep handlers, and I've highlighted the relevant changes with respect to the deep handlers again. So like a shallow handler, the body of the resumption doesn't have to re-invoke the same handler, but on the other hand, we actually parameterize the resumption by the handler. And here the handlers have to be kind of first-class things that you can pass in as arguments. So this means that each time you run this R, you can insert a different handler if you wish. And then what else changed? Oh yes, this, you see the change in the resumption type as well. Here's this first-class handler is passed in. So that tells you how you're going to proceed. In common with a deep handler, however, the body of the resumption, it does have to invoke some handler. So kind of the intuitions you might think of here are that with shallow handlers, it gives you kind of maximum flexibility to reflect on the structure of this tree as much as you like, but that gets in the way of nice algebraic properties and reasoning and optimizations. And these sheep effect handlers are somehow somewhere in between. As it turns out, you can express all of these in terms of one another, but at the cost of various administrative reductions, which can be terrible in practice. You can end up with terrible memory leaks, for instance. Anyway, this is all maybe a little abstract, so I'm going to move to a concrete example to show you how these things work. So lightweight threads. This is what I see as one of the killer apps of effect handlers, implementing various forms of concurrency. Now I picked the simplest one I can think of. We have a single effect operation called yield. It doesn't actually have any payload. It doesn't return a value. I mean, it goes from unit to unit. And the idea is that we're going to write some threads, and when they're willing to give up control to another thread, you invoke yield. And then the scheduler, which will be a handler, should re-invoke, should resume the computation at some point in the future, you hope. So my simple example is I have a couple of lightweight threads that are going to interleave printing some things out with a couple of yields. And we're going to pass these into a handler so that they run together. In practice, we may well want to extend this with, say, a fork operation so that we can dynamically fork off new threads, but I'm keeping this simple for now. I'll actually show you an extended version when I get to the WebAssembly in a minute. So here is an implementation using deep handlers. It's based on, for convenience, I've defined a couple of type synonyms here. You actually see that we need a recursive type. So a thread is just a thunk that can perform the yield operation. But we're going to need a data type of resumptions that are parameterized by the list of all the other resumptions. So that's similar to a thread, except the yields have been handled here, and it is parameterized by the list of all the other resumptions. So then the handler we're going to define, it takes one of these threads and it returns a function that is parameterized by all of the other resumptions, and then it will handle this thread effect, the yield effect. And the implementation is fairly direct. So we have the return. In the return case, that's when this particular thread has finished. Well, we see if there are any more to run. If there aren't, then we just stop. If there are, then we move on to the next one. And the resumption is expecting a unit, because that's the return type of yield. And our return type tells us we're also expecting the list of all the other resumptions. So we just pass that in. More interestingly, if we do a yield, then we get the resumption of the current thread, and we see if there are any other threads. If there aren't, then we just carry on running the resumption because there's no other ones to run. But if there are, then we switch to the one at the front of the queue of threads, and we stick the current resumption onto the end of that queue. In order to use this, it's convenient to have a couple of helper functions. The things that we actually write are likely to be a thread type rather than the res type, but we can lift one of those, lift a thread to a resumption, basically by just handling the thread with our handler. And then the thing we're going to start off with is a list of threads. So we want to map over that list. We want to lift all of those to resumptions. And then just to make it easy, we start by running the identity thread, which will then immediately finish and run the first one in this list. So if we, having written something like this, just a few lines of code, we can now get our threads to cooperate, and they behave as we expected. It's interleaving the A and B threads while returning the unit value. Now I'll show you how this looks with shallow handlers. So yeah, actually a crucial thing to see here is that there's no explicit recursion here, because that's hidden in the fold that is performed implicitly by the R, because the R invokes this handler over and over again. In contrast, if we do this with shallow handlers, things get simplified actually somewhat. We have the thread and resumption types are the same here, and instead of parameterizing with through having the handler return something that's parameterized, we can actually just use a recursive function. But each time, right. So we handle the first resumption, and then each time we need to change, we just reinvoke this recursive function. And again, you get the same behavior. Now, just to illustrate how these sheep handlers work, well, we do end up needing a different type of resumptions. Again, it's more like the deep handlers, but you also have some recursion going on, and crucially, you can see that each time you invoke the resumption, you could plug in a different handler here. In fact, we're not doing, because this is a deep handler, but it gives you this extra flexibility that you could use if you wanted to. But otherwise, it's quite similar to the deep handlers. Okay. So there's my crash course in effect handlers for doing concurrency as a high-level programming construct. Now, the idea with WebAssembly is we wanted to add these as a low-level construct for other people to compile their source languages into. But first of all, I should just say a little bit about what WebAssembly is. So it's a low-level language and execution environment, and it's got a formal semantics. It's actually, the semantics is fully mechanized in several different proof assistants, and any extensions to the language have to be given a semantics and proved correct, which is unusual for these kind of industry standard things. It was originally conceived for use in web browsers, and all of the main web browsers do support it, but it's also used more broadly in other areas, such as content delivery networks. Right, but as Andreas Rosberg, who was one of the creators of WebAssembly, says, it is neither just for the web, nor is it actually an assembly language. It's a bit higher level than that. You might think of it as sort of analogous to something like the JVM or .NET, but explicitly supposed to be designed to cover a broader range of languages, not just one specific language. So there's work on adding effect handlers to WebAssembly. I've been doing that with these people. We internally called our system WASM-FX, but the actual official proposal we've put forward is called typed continuations for various sort of non-technical reasons. And it's a possible implementation for what the WebAssembly community know as stack switching. Unlike the presentation I've just shown you, it features an explicit continuation type rather than just using functions for these resumptions. It's also restricted so that the continuations are expected to be linear. There's not a type system to do that. These are checked dynamically. And there's not actually a separate handle construct. If you want to handle a continuation, you create a continuation and then you resume it. At which point you can say how to handle it. And each time you resume the continuation, you get to change the handler. The design, unlike maybe sort of typical implementations of effect handlers, is specifically designed to support reference counting. It doesn't need full garbage collection. Right, now I'll give you some details of what it looks like. So we have this continuation type. I'll show you what this type index thing is later. We have control tags. You can think of these are basically operations, and you get to declare the signature of the operations here. That's what the tag indexes are. And then there's three core instructions. One creates a new continuation from a function. The other one suspends the current continuation. So this is basically corresponding to performing an operation. And then resume corresponds to running a resumption or a continuation. But it has an extra, you provide an extra argument to this, which is the handler. You also take the continuation arguments here, which I haven't put there. But there's also some additional instructions. I'm not going to talk about those. Now I'll just go quickly through expanding out what these things look like. And I realize that the syntax may look quite odd if you've not seen WebAssembly before, these dollar things are used to indicate names or variables. You have a list of parameters. The star indicates a sequence of 0 or more things, and a sequence of result types. It's and often these kind of types are denoted in this way in square brackets. WebAssembly has a stack discipline, and the types basically type what a particular instruction does to the stack. So suspend takes one of these tags, and it takes some things off the stack and puts some things back on the stack. So these correspond to the types of an operation. Right. Cont.new, so that takes a reference to a function and gives you back a reference to a continuation. So the special continuation reference type that we've introduced. And then the more, like most of the work, happens in resume, as I said. So resume takes this list of pairs of operations and labels. So this defines these operation clauses. And a label is just a pointer into the code. Right. And yeah, it takes a reference to a continuation, and also the arguments that continuation is expecting. And it gives back the return type of that continuation. And these operations all have to match up with the types of the labels. So the labels correspond to some part in the code, and it's telling you what should be on the stack before you get there, and how it's going to change the stack afterwards. So I don't think you don't need to understand all the details of this. I don't have much time. So main thing is that there's no handle construct. You've just pulled that into this resume construct so that you can change every time you resume. Oh yeah, I wasn't going to talk about this. I won't talk about this resume throw instruction. And then when you write a typical handler, it looks quite weird like this. But what's interesting about this is it's structured like a scheduler loop that you might write in an imperative language, and it's written in an entirely imperative style. So this defines a loop with the label L, and you see all these branches to L, which are going to take us back up there. Now, let's see where the handler is. So the resume, the handler itself, is actually this thing, and you see that each operation maps to a label, and the label is attached to these blocks here, which are parameterized by their result types. But what this is saying is, if at some point, so in this ... we do a suspend, then it will jump to the appropriate point after these comments, so the end of the corresponding block. So it's kind of a bizarre syntax for the same thing we started off with handlers, that fits nicely with the WebAssembly design, and also allows integrates with the type system. Okay, so yeah, again, that's a bit abstract. So maybe here's an example: lightweight threads. So I've actually done, as well as the yield instruction, I've also done a fork instruction, and you can see what we have here. We're assuming we have a queue of resumptions or threads. We check to see if it's empty. If it's empty, then the loop just stops. Otherwise, it's going to call resume on the first one, installing the appropriate handler. So that's going to actually switch to the stack corresponding to that new thread. And then when that's done, it's going to bind this next k variable to the next one in the queue. And if it comes upon a yield, then you enqueue the current continuation and set next k to the next one at the head of the queue, and then just go around the loop. And then fork is going to just do something similar. It's going to enqueue the new thread and continue. So yeah, I mean, there's just, I guess the point is just to show you that this idea of effect handlers nicely transfers over to this low-level WebAssembly construct. We have lots of other examples: lightweight threads, actors, async await, for instance, and it seems to give a pretty clean way of implementing a whole load of features that people really need at the moment. Right, I'm not going to talk about the other instructions I said, but I am going to finish up by telling you where we're at with this design. So we have an extension of the WebAssembly reference interpreter that implements all this. We have a formal specification. And like I said, there's a whole load of examples. And the next steps include mechanizing the specification. We're in the process of implementing at least a basic unoptimized version of the implementation in a more realistic implementation, WASM time, which is a standalone implementation written in Rust, which is reasonably accessible. So we're hoping to get that done over the summer. And then we're going to build a number of backends for some of our research languages, and maybe some other languages too. And there's all kinds of awkward design considerations which we can't really address properly until we've run some benchmarks. So people in the WebAssembly community are very concerned about performance, which has in a rather brittle situation where you might be taking code from lots of different languages, some of which might have GC and some of which might be using reference counting. And we want to support reasonable defaults for all of these things, which may, well, we don't know how it goes until we do some benchmarks. Another nice thing about starting from this like well-studied mathematical foundation is that we already know how to do a whole load of different extensions, and we can take some of that from take some ideas from ongoing work on algebraic effects and effect handlers. So there's some of them, but I'm gonna finish here because I think I'm short on time. And yeah, if anyone has any questions, then please ask.
Yeah, very nice talk. For online attendees, if you have questions, you can just unmute yourself. Yes, please go ahead, Eugenia.
Thank you for the presentation. I have a question regarding the first part about handler. So usually with effects, you have also some equations. So I was wondering, and therefore I would expect that you need some proof obligation in order to ensure that a handler respects these equations. Have you investigated that?
Yes, but yeah, for this work, we've just kind of completely ignored the equations. So in the original work on effect handlers, equations were absolutely crucial because that's what algebraic effects give you. But then in a lot of the practical implementations, what has happened is the programming languages don't have facilities to do the reasoning about the equations in the language. So they're not checked. So basically we're just working with free theories. But yeah, if you want to validate a particular implementation, then you absolutely want to check the equations. Mattia Pretner and his student Giga, they've done some work on actually integrating the equations back into the practice of programming with effect handlers, but that's not something I'm considering here.
Okay, thank you.
Gabriel has a question in Paris.
Yes. So the typing rule for sheet handler, it looks a bit constrained because you ask that the handler you pass when you resume be from type G to D, and it looks like you could have more flexibility in the typing rule. I wonder if it's
Sorry, what's
in the
I think you have to speak very loud.
oh yes, okay. The resumptions are it takes something that goes to D and returns the D. But could it be something more flexible? Because at the call site, I decide what resumption to pass, so I could go to another site than D and then fix up the result afterward.
Yeah. So I mean, so there's very strong connections between delimited control and effect handlers, and answer type modification is a thing that you have with delimited control operators, and you can absolutely do similar things here. But we're just working with the simplest form of these things for now. And then we have a very impoverished type system in WebAssembly anyway, so that's not something.
But I suppose that in WebAssembly you are enforcing R to be called in fail position, something like that.
Yeah, WebAssembly you essentially, well, we can look at the rule probably. If you look at the if you look at resume, you see that these types have to line up, S1 and S2 and S1 and S2. But yeah, often in practice you end up having to box your types anyway because your source language is much richer than what WebAssembly can provide, and that's one of the kind of challenges. There are some people who attempted to, I don't know, add a linear type system or an effect type system to WebAssembly, but that's not going to fly.
Hi Sam, this is Max. I actually had a question about the same rule, the sheep handlers. So the deep handlers rule comes from the universal property as a free monad, and then the shallow handlers comes from the universal property as being a coproduct. So is there a universal property that this rule corresponds to? Because then you could get a beta and eta rule for it.
I hope so, but it's not something I've thought about at all. Yeah, I mean, these things arose entirely pragmatically, and we haven't really thought about the theory at all. I just retrofitted the typing rules and the abstraction based on the design we had for WebAssembly. But I think, yeah, it might be worth investigating.
It looks kind of reasonable. It looks like there's a continuation monad going on. So something. Okay, thanks.
Thanks.
Yeah, I think we can take one more question from Paris. Yes, please go ahead.
So, hi Max. I wanted to ask as well, you mentioned Coca was one of the, so actually maybe this is a question for the chair. I thought that Coca has a nice compilation story for control operators that does not require any backend support. So why do you care?
Right, that's a very good question. That amounts to doing a global CPS-like transformation, which works fine, but it's not very good, say, if you want any kind of modularity or interoperability story. So I can confirm, I mean, Dan Lyon, who does Coca, is one of the people who's very much involved in this. Well, as is Ning Ning to some degree. And Dan is very keen to have this so that he doesn't have to use the nice story that Dan and Ning Ning worked out for the case where you don't have low-level support. And the reason that Dan did that is because he didn't have a suitable target that he could pick instead.
Okay, thank you.
Great. Let's thank the speaker again.